Here I'd like to talk about various ways of comparing sets, the first of which is the idea of two sets being equal. Here's the definition. Two sets A and B are equal, and we just write the normal equal sign between them, if that's what we mean, if they have exactly the same elements. It's the simplest idea of equality that you could possibly come up with. If the sets don't have exactly the same elements, we write A is not equal to B. Some examples. If I had the set containing the elements 1, 2, 3, and 7, and I wanted to compare it to the set containing the elements 1, 7, 3, and 2, I could say those two sets are equal because they have exactly the same elements. There's a 1 here and a 1 there, a 2 here and a 2 there, a 3 here, a 3 there, a 7 here, a 7 there. There's no element here that's not over here. There's no element here that's not over here. So those two sets would be equal. This is probably also a good time to point out that order is not important in set notation. So the fact that they're not written in the same order makes absolutely no difference. Here's an example of two sets that would not be equal. There's an A here and an A here, but the B here is not doesn't show up over here, and the E here doesn't show up over there. So if there's any difference at all in the elements, then the two sets are not equal. Another comparison amongst sets is the idea of one set being a subset of another. And here's the formal definition. Set A is a subset of set B, and the way we write that is to take set A and then write the symbol as sideways U with an underline and B on the right. So the set that we're calling a subset is on the left of the symbol. In any case, set A is a subset of set B if every element of A is also an element of B. Let's look at some examples of that. If I have the set consisting of the elements A, B, and E, and I'm looking to see if it's a subset of this set containing the elements A, B, C, E, and G, the condition is every element in A, this is the set A, also has to be inside of the set on the right, which we're calling B. And it's easy to see that that's true here. There's an A here, it reappears over here. There's a B here, you see it there. There's an E here, there's an E there. So this set on the left is a subset of the set on the right. Second example, and try the same thing. There's an A here, it appears on the right. There's a B on the left, it appears on the right. There's a C on the left, it appears on the right. There's an E on the left, there's an E on the right. There's a G on the left, and there's a G on the right. So according to our definition of subset, the set on the left is a subset of the set on the right. Now it might look a little unusual that the two sets are actually equal, but that's okay. This still satisfies the definition of a subset. So a set is in fact a subset of itself by the definition of a subset. That's something to keep in mind. Two things that aren't subsets, one's not a subset of the other, would be, for example, if you had the set, which we might be playing the role of A, whose elements are dog, cat, and you have the set that's playing the role of B, which has elements dog, pig, and goat. There's dog on the left and on the right, but there's no cat in set B. So we would say that the set consisting of the elements dog and cat is not a subset of the set consisting of dog, pig, and goat. If there's any element on the left that doesn't appear on the right, you don't have a subset. There's a closely related term called proper subset. So I need to emphasize that word, proper subset. A set is a proper subset of set B, and you write it the same as for a regular subset, except there's no horizontal line which stands for the equal to part. So you'd write A and then a sideways U to B, and that means proper subset. A set A is a proper subset of a set B if every element of A is also an element of B. Now that's the same as for a regular subset, with this extra condition that A and B can't be equal to each other. So these are very similar definitions, but the proper subset does not allow equality. So again, looking at some examples, if you have the set consisting of the elements A, B, and E on the left, and the set containing A, B, C, E, and G on the right, you can see there's an A, it appears on the right. B appears on the right. E appears on the right. So you could say that the set containing A, B, E is a proper subset of the set containing A, B, C, E, and G. However, if you look at this second example, there's an A that appears on the right, that B appears on the right, that C appears on the right, and that E appears on the right. So the set containing A, B, C, E is a subset of the set containing A, B, C, E from the previous definition, but it's not a proper subset because a proper subset does not allow them to be equal. So it's the same idea as a regular subset, except it throws out the one case when the two sets are equal. One more example. If you've got the set containing the elements D and C and you're comparing it to the set containing D, P, and G, there's a D on the right, but there's no C on the right. So that's not a proper subset. It's not a subset, nor is it a proper subset. It's the idea of a subset versus the idea of a proper subset. Before I leave that topic, I want to say one more thing about it, and that is you need to pay really close attention to the difference between those two things. Regular subset, which we just say subset, or proper subset. And I would suggest maybe an analogy is appropriate here. Sometimes an analogy to something that you're more familiar with can help you. I would compare it to the difference between using the less than symbol and the less than or equal to symbol. And what I'd say about that is just as less than or equal to allows the possibility of equality, if you have the horizontal underline, that also allows the possibility of equality if you're talking about subsets. And remember, a proper subset doesn't allow the sets to be equal in the same way that less than doesn't allow things to be equal. And just to see that actually sort of an example of that, suppose you go back to some statement like this. I can say 5 is less than or equal to 5 and get a true statement, because the equal to part allows for the possibility of being the same. But if that equal to part were not there, that would not be a true statement anymore. That would be false. 5 less than 5 is a false statement. So that underline that stands for equality is what makes the difference. So in the same sense, if you're working with sets and subsets, I can say the set containing 1, 4, and 7 is a subset of the set containing 1, 4, and 7 because of that possibility of equality represented by the horizontal line. Again, if I take out the horizontal line, that becomes a false statement. The set containing 1, 4, and 7 is not a proper subset of the set containing 1, 4, and 7. So the difference there, to me, is analogous to the idea of less than versus less than or equal to. Maybe that'll help. Moving along, we can also ask the question, how many subsets can a set possibly have? And I'll just go ahead and give you the answer. A set that has k elements has 2 to the power of k subsets. For example, if I took the set containing the 3 elements A, C, and F, the number of elements is 3. You take 2 to the power of 3, that's 2 times 2 times 2, there would be 8 elements. So that's the way you tell how many subsets you have. I do want to actually list them here just to see, so you can see how this works. And before I do, I want to make one note here that I want you to pay special attention to. That is, the empty set and the set A itself are both subsets of any set. The empty set is a subset of every set, and a set is always a subset of itself. So if you're going to write them all down, if you've got a set with 3 elements, the biggest a subset could be would be the whole set would be 3 elements. But you could have a 2-element set, a 1-element set, or you could have a set with no elements. And because I've already told you that the empty set is a subset, the only 0-element set would be the empty set. So you can go ahead and put that in automatically. And the only 3-element set will be the set itself. So you can go ahead and put that in. Now we're tasked with finding how many 1-elements, or actually writing out the number of 1-element sets and writing out the 2-element sets. Well, it's easy enough. The only 3 sets that have 1 element are each element listed individually. So the set containing just the A is a 1-element subset. The set containing just B is a 1-element subset. Oh, excuse me, there's a C, not a B. And the set containing the element F is a 1-element subset. How about the 2-element subsets? Well, you just have to be careful, but we can do that. You could take the A and pair it with the C. That would be a 2-element subset. You could take the A and instead pair it with the F. That would be a second subset of 2 elements. And if you think about it, the only other combination would be the C paired with the F, because remember, order does not matter. Doesn't at all matter what the order is. And if you count them, 1, 2, 3, 4, 5, 6, 7, 8, just as we said. There are 8 subsets for any set that has 3 elements. The last concept that I want to cover here is the idea of equivalence of 2 sets. And here's the definition. 2 sets A and B are equivalent if the 2 sets have the same number of elements. That is, if the number of elements in A is equal to the number of elements in B. Now that's a very simple idea, but let me try to make you understand the difference between equivalent and equal. And I think maybe the easiest way to do is, again, through an analogy. And I'm going to use the old clock analogy. Analog clocks are often labeled with their numbers just using regular Arabic numbers 1 through 12. But some analog clocks actually use Roman numerals. You've probably seen them. You would have a clock that would look like this, Roman numerals 1 through 12. But the time of day doesn't change based on which label you put on these things or which name you call them. So the analogy I'm thinking of is something like this. Perhaps the best way to think about the equivalence of 2 sets is to think of the elements as simply names or labels. And it doesn't matter if you use the Arabic numeral 1 or the Roman numeral 1 here. It doesn't matter if you use the Arabic numeral 6 or the Roman numeral 6. They're analogous to each other. So in that sense, we would say that set A and B are equivalent to each other. Not equal to. Equal to, they have to have exactly the same elements, and no matter how you think about it, this element, Arabic 1, is not the same as any element down here. So you can't say equality. Equivalent is like a one-to-one correspondence. This one corresponds to that one corresponds to that one. You can set up a one-to-one correspondence, and that means they have the same number of elements. So equivalent is definitely a different concept than equality. Equality requires the sets to be not only the same size in terms of having the same number of elements, but they also have to have exactly the same elements. Equivalent is a less strict condition where you simply have to have the same number of elements. And to make my point one more time that all you're doing with equivalence is counting the number of elements, here are a couple of examples. If I have a set with the letter A, the number 2, the number 5, and the letter F, it would be equivalent to the set containing dog, cat, bird, pig, even though they don't have any elements that are exactly the same. They do have the same number of elements. There are 4 elements in this set, and there are 4 elements in this set, and that's all you need for equivalence. So they are equivalent. On the other hand, the set containing P, Q, and X has 3. The set containing A, 2, 5, and F has 4, and so those two are not equivalent. So the idea is simply count the elements in each.